will talk about two related but at the same time different connected but different material systems and devices. One will be about a very particular kind of amplifier that we have recently demonstrated, and the other device is a bolometer, and both of them, what connects them is that they're both using materials which are either 1 atom thick or 1 or 2 unit cell thick. So I'll try to explain that as we go along. The details are in this paper, which you can access from our webpage, which is here. And I gratefully acknowledge the funding that we get from Department of Atomic Energy through TIFR and Department of Science and Technology and SCRB, which makes this work possible. Okay, so, okay. Oh, I see. Oh, okay. All right. So, of course, I'm giving the talk here today, but I'm grateful to have collaborators and students and staff working with me, who really are sort of truly the ones deserving of the credit for all this work. And this is a photo from a recent trek to Ratangad that we took with the group. So the two people whose work I'll talk about together with other people who are contributing is Sanat Ghosh. He's a PhD student finishing up, and this other person is also a PhD student, Joydeep, and they have worked on these two different projects. The people who have been part of the team which really made this possible is Digambar Jangre, who's a scientific staff in the lab. Other students, Supriyo Mandal finishes PhD. Shubhamay Ghatak was a postdoc a couple of years ago. Alicia and Ipsita were JRF or project students working with us. For the work related to amplifiers, that work was in a very close collaboration and with Vijay's lab, and some of the key ideas and expertise is Vijay's. Vijay is a kind of renowned world expert in these parametric amplifiers, and he has been developing key ideas for a number of years. So this collaboration was really very fruitful, and Vijay's student Kishore was involved in really doing some of the key measurements together with Joydeep. And for the other experiment, we use high TC superconductors, which are actually grown in Tamil Wales group together with Ruta. So their really work makes this possible. And we use a high quality hexagonal boron nitride, which is made by Dr. Watanabe and Taniguchi in NIMS, Japan. And so I want to make sure this is something we use for the heterostructures that I'll explain later. So these are the people who really make the work possible. I have a relatively peripheral role in making these scientific results possible. So let me quickly tell you a little bit about what we do. We work on a lot of different aspects, and now largely two-dimensional systems or physics of two-dimensional materials. We look at devices which are layers of 2D materials, either twisted with relative to each other. They're called tristronics. I talked about this in a colloquium a few months ago. We work on nanomechanics, now less so than before, but an area that we are interested in is something unique that happens to magnetism in 2 dimensions, magnetic excitations of 2D materials. Then what's happening? Sometimes it works, sometimes it doesn't. Okay, strange. It's advanced here, but not on the screen. Okay, so there's a lag between the Zoom. So this has got frozen. Okay, that's okay. So we work with 2D superconductors and graphene-Josephson junction, and today's talk will have two parts, which will focus on the graphene-Josephson junctions, which be used towards making amplifiers, and 2D superconductors, high TC superconductors will be used as bolometers in the second half of my talk. So let me get started. This is my rough outline for my talk, and please feel free to interrupt as we go along. My aim is to finish by 5, but I'm happy to have questions. So I'm going to first part rather, I'm going to talk about a particular kind of RF amplifier which can be made using graphene-Josephson junctions. I'll try to say why these amplifiers are needed. There are lots of amplifiers that are available. What's the unique aspect of this amplifier? And these particular amplifiers are called parametric amplifiers. So this idea itself is very general, but I'll try to explain what it is and then talk about our work, which is sort of the performance of these amplifiers. Then I'll talk about these bolometers made using high TC superconductors, and why these are needed. There's a sudden spurt of interest in these bolometers or nanowire detectors, even in high energy physics, as I will explain later, for detecting not just radiation, but also other particles for searches of dark matter. Then I'll talk about our work, and I'll say a few words. I won't have a slide, but I'll talk about what are the possibilities of future experiments in both of these projects. So, so amplification, or you would imagine that if you want to measure something which is feeble or very small, and if there is a lot of background, you want to be able to sense that feeble signal, then you want to necessarily amplify it. And easiest way is to think of a megaphone or something. If you're, it's a crowded room, then you would use a megaphone to amplify your sound so that it's heard easily. And an area where detecting feeble signals is very critical, and this is actually sort of the domain of QMAC group led by Vijay, which is measuring quantum signals from qubits and their complex architectures. These electrical signals that come out of these devices are very, very small. Okay, so powers that are something like roughly about 10 to the power minus 16 watt. So these signals are very small, and their devices are typically sitting at very low temperatures. And eventually, when you want to bring them out to room temperature, the signal you want to record or manipulate, you want to have signals of the orders of milliwatts. So you want to amplify the electrical signal, and also the temperature at which you do these measurements, sort of eventual recording is at room temperature. So, that's where the amplifier comes in, that if you have some electrical signal, you amplify it. And the defining property of an amplifier is that it increases the amplitude of the input signal, which is reflected by the parameter of the amplifier, which is the gain. And invariably, every amplifier will add a noise to the amplification. This is not just a property of this amplifier, but any amplifier. It will add some noise to it, and the measure of the noise is a parameter called the noise temperature. Okay. So smaller the amplitude of the noise added in, the noise temperature is smaller. So this is one way to benchmark the noise. And so this is how the amplitudes are related through the gain. Now, typically in any electronics, certainly electronics of these devices, you don't use just one amplifier, but you use a chain of amplifiers. So there's an amplifier with like the JPA, Josephson parametric amplifier. Then there is an amplifier which is a Hempt-based amplifier, which has a typical noise temperature of about 4 or 5 Kelvin. And this parametric amplifier is desirable to have its noise as small as possible. So it's typically, as I will show later, also is around 0.5 Kelvin or less. So now, why is it that the first amplifier has to be sort of the one which adds the least amount of noise? So if you have a complex chain of amplifiers, and this could go on further, then the total noise that is added into the system reflects the noise temperature of the chain of amplifiers together with the gains. And the most important part to notice is that the noise temperature of the first amplifier is there no matter what. So it basically sets the overall noise added to the system, and the gains of the amplifiers and the noise temperature of subsequent amplifiers will also come in. But you want this to be as small as possible, because this is going to essentially set the reference and then some additions to it. So you want an amplifier at the first stage which has the least amount of noise possible that you can think of. And that sort of is the motivation for this Josephson parametric amplifier and how people devised it. So this idea of parametric amplification is very general in physics and has been around for a long time. And the superconducting circuits community, some of the sort of foundational work was done. Vijay was a graduate student at Yale using these JPAs for superconducting circuits. So I'll explain. So before I go into it, so these amplifiers were realized using aluminum-based, so I would call it at this point technology, aluminum oxide-based Josephson junctions, and they allowed lots of interesting experiments possible with detecting properties of qubits, and this is sort of studying properties of charged qubits more recently. So they have played a critical role in a lot of, I would say, quantum processing. And so the natural question is, you might say, if they already existed before our work, then why should one, kind of expend resources in trying to make another kind of amplifier? And that's a very valid question to ask. So there are kind of reasons where one wants to make an amplifier which will work with a prospect of using them at high magnetic fields. Instead you have want to have tunability. I will explain what tunability means. Tuning its center frequency with electrostatic gate rather than some other knob. And I think something that we are quite excited about is trying to make new kind of sensors where using different 2D materials which can use different properties of 2D materials, which facility is not there for aluminum-based Josephson junctions. Okay, so that's sort of the reason why we want to do things like try to make new kind of parametric amplifiers. So just to give you kind of a broad introduction to parametric resonance and amplification. So if you think of a oscillator, a mechanical oscillator even, you can write down a simple equation to describe the response. In this case, it's X is just the amplitude, spatial amplitude, if you like. Now, you can devise situations, and I will explain this in a minute, where you can parametrically drive the system. And so one way to think about this parametric drive is if you have a mass attached to a spring, and the spring constant of the system itself so parametric, this is kind of important. If there's a spring constant, which is we know as mechanical spring constant, if there is a way to modulate or the spring constant dynamically, then you can realize this amplification. So imagine a spring constant which you can externally modulate or modify. Then you have a parametric kind of resonance. And one nice way to kind of see this, visualize this, is that because of this modulation of the spring constant, so this is related to the K, you can see that the amplitude has a denominator similar to this, but then the damping term is reduced by this delta. So if you modulate the spring constant with an amplitude delta, what you're effectively doing is whatever is this damping term, which is the viscosity or which determines the quality factor of the system, or the losses in the system, then you can reduce that by this parametric process. Now, what's a nice example of this, and a nice example of this is, how you're in a spring, and by the sort of way at which you move your center of gravity, you are essentially parametrically driving the swing and increasing the amplitude. Okay, and that's basically this thing happening in a way that's sort of intuitive to us. You increase the amplitude, overcoming the losses in your, and there are sort of implications of this in kind of really optics and other aspects where you can have a cavity where the cavity is actually being modulated. The cavity length is modulated at some frequency, and you can realize amplification. Okay, so this is sort of related to this idea of optomechanics, a wide field where people have done experiments. So this idea of mechanical parametric amplification is very useful and has actually been used to make mechanical sensors which are very more sensitive than they were before you parametrically amplify the signal. So this is work done several years ago by Dan Ruger's group, looking at essentially cantilevers, and they were trying to detect spin of a single atom using cantilevers. And we did some experiments now 6 years ago, which essentially did this parametric amplification and nonlinear physics of one atom thick graphene membrane, but just looking at the mechanics of it. So they have intrinsic some nonlinearities which allow essentially similar physics to be seen mechanically. So this idea is very general, starting from mechanics, optics. I won't really talk much about optics, but it's used quite a bit. So today we are going to talk about this parametric amplifier, which is based on superconducting circuits, which the key component of this circuits is with this symbol. It's called the Josephson junction, and it will have some capacitor in parallel and possibly some resistance shunt in parallel as well. Now, when you have what a Josephson junction is the simplest Josephson junction is the you have a superconductor, an insulator, and a superconductor, And this was in the original paper of Brian Josephson. If you have this and the insulator is thin enough, then the wave function of the macroscopic wave function of the superconductor sort of overlaps, and you get a supercurrent going through the junction, actually through the insulator. And that physics led to the Josephson physics. Now, the physics that I will talk about is, again, if it behaves like a Josephson junction, but it's like superconductor separated not by an insulator, but by some normal material. This I don't have on slides, so I thought of differentiating. So now if you write down the circuit and you're driving a current through this circuit, then the property of this simple Josephson junction based on the tunneling is that it has a relationship with the phase across the junction, and some current will go through the resistors and some displacement current through the capacitor. So this is the total current, essentially kind of a Kirchhoff's law of this three components in parallel. And now if you try to simplify this, okay, internet connection is unstable. Fine. So this is what it looks like. So now if you externally try to drive this system, this whole system of equations actually is very similar to the equation of the swing or the mechanical oscillator. The physics is similar, not the same. This phase phi is a little bit more a subtle quantity, but instead of just phi, this in a mechanical oscillator, which here it's sine phi. And the fact that it's sine phi has important consequences and helps in realizing these amplifiers. So the sine phi term in a kind of expansion can be written down like this. So it contributes to higher order terms, which kind of play an important role in the response of the system. So I won't spend too much time, but what I would say is that presence of this term essentially allows you to do the same kind of thing, which is like having the spring picture to modulate that parametrically, and sort of you can write this. If you apply some signals, you can pump the system to have a kind of a sort of modulation of the spring constant, and then you can realize amplification. And this nonlinearity in the sort of higher order terms is key to giving rise to this physics. Okay. So this is the circuit of interest, which is some Josephson junction in the technology based on aluminum oxide is often as squid. So the advantage is this becomes tunable. If you apply a magnetic field, then this frequency of oscillation is tunable with external magnetic field. So these are sort of oscillators, rather parametric amplifiers, which have been made with realizing aluminum oxide separated squids or Josephson junctions even, and they have been used quite a bit. And in fact, for most of their measurements, Vijay's group uses these params based on aluminum oxide based sort of design. So very simply, how does the amplifier work? So as I sort of try to simplify it, so this potential, when it's not harmonic, if it's a complete perfect parabola, then this physics actually, or this amplification process doesn't really work. But the fact that it's unharmonic means that if I drive this system to larger and larger amplitudes, I will sample the fact that the potential is not harmonic, and that's key. Whereas if I drive it at very low amplitudes, you can approximate it as harmonic. So to see this amplifier, you have to actually drive it to high powers to sample those nonlinearities, which makes this amplification process possible. So if you think in terms of the small signal kind of way of thinking, the way this device works is that if you use a Josephson junction shunted by a capacitor, it gives rise to a resonance, just like a Lorentzian which is a response of the second order equation. And this is how it will look if the system doesn't have any nonlinearities. But the harder you drive the system with a stronger pump, it will sort of sample the nonlinearities, and the response is no longer Lorentzian. Why is this not? No longer Lorentzian, but it actually, depending on the sign that you have, because it's sine phi, you get a negative alpha x cubed term. It sort of bends in this one direction. So it will, at large amplitude, it will be like this, and there is this very peculiar point where this part of the slope of this curve is actually near vertical. Okay, that's a peculiar point called the bifurcation point. And after that, the response of this system, if you look at it in terms of it's multi-valued at a given frequency. Okay, so the point of interest is just before these multiple solutions of the system become possible, and the amplitude response looks like this, more like this orange curve. So now, if you have biased it by sending some pump signal at this point, then if you put in another signal of a small amplitude at this point, then it bounces off this very sharp, steep slope, and it comes out amplified. And that's sort of the essential idea of the amplification in these parametric amplifiers. So the sort of the geometry that we use in our devices is graphene contacted by two superconductors, and by contacting it with superconductor and under the right conditions where these contacts are transparent, you can essentially inject. It's as if your composite device has a supercurrent, a dissipation-less response. So people demonstrated this first time with graphene in a ballistic geometry with this. So what happens is you take graphene, and I'll explain how the device is made in a few minutes, but you have a region where black region is, there is no dissipation in the system. And it's because of the formation of Andreev bound states. At this point, we don't need to know the details of it for understanding this talk. So this region where it, even though there is graphene, which is normal in itself, but by contacting it with superconductors, you can essentially realize a superconductor like response using the Josephson junction. And the magnitude of this critical current is tunable with electrostatically with a gate. So the gate is electrostatically changing the number of charge carriers in graphene. And I'll explain that a little bit in the next couple of slides. So this is one side where the conduction happens because of electrons, and this is holes. There are some asymmetries at this point, and you'll see that in our devices. This is not our device, and I'll try to explain, but it requires some technical details, which depending on time I might skip. So what happens is in these Josephson junction, which is SNS kind, which is superconductor sandwiching a normal material, which is graphene, the relationship between current and phase is somewhat more complex. It looks like this, whereas in the case of simple tunnel junctions, like the one aluminum and aluminum oxide in between, the term in the denominator is actually not there. These terms, prefactors are different, but it only depends on sine phi. So in our devices, there is some additional physics, but it certainly has the system nonlinearity to allow. So if I had used a sort of textbook inductor, then the potential, if you like, or the problem is harmonic. And in this case, and in the case of aluminum oxide tunnel junction, so basically for all kind of Josephson junction, the problem is unharmonic. So the energy levels are not equispaced. This is not, the fact that it's unharmonic is important, but this energy level part is is more relevant when one thinks about trying to make qubits out of Josephson junction that Vijay has talked about very nicely earlier in his talk. So I'm going to talk about that stuff. So in the last several years, there has been a lot of interest in using these devices to make tunable inductors. So now you have an inductor whose value can actually be tuned with an external voltage. So you just send in a voltage, just like you have a transistor whose conductance changes with a function of gate. This is an inductor whose inductance value changes as a function of just a voltage that you apply. Okay, so people have demonstrated not just simple an inductor, but they've even tried to make qubits out of this graphene Josephson junction. They're not great, but thinking about this article work actually led us to think about whether the fact that these are not good qubits may still allow them to be good ingredients for amplifiers. The other part, which is sort of has also got a lot of attention recently, is trying to make graphene bolometers, because graphene has a very low specific heat. So if you have something which is very low specific heat and some radiation lands on it, then the effective change in, say, for example, the temperature would be large. So people have tried to look at this a lot in the recent years. And although we won't talk about this here, but one of the things that we are interested in using this kind of technology to make new kind of bolometers.
Just anharmonicity or asymmetry in the potential?
Anharmonicity.
Q to the power 4 then also what?
Q. No, okay. No, we want asymmetry. We want an odd term so that it will list to one side. So in mechanical systems, this is called duffing nonlinearity. So you can have nonlinearities which are bending to the other side and sometimes on the left. But the fact that it's cubic is very important. I think there can be other contributions, and people have tried to quantify it. So, okay, let me go back. So, oops. Okay, if it can automated, if it's can stop. So how do we make these devices? I've talked about similar processes. So we kind of peel off layers of these 2D materials, which are essentially some more sophisticated version of using your Scotch tape. You can peel off graphene and know how many layers is it uniquely by a number of different methods. You can peel off hexagonal boron nitride, and the assembly is really kind of very exquisite hand-eye coordination and skill, which I don't have, and I'm grateful to have students who have much better skill. And you basically assemble it by using a transparent plastic or polymer. So you pick up one layer, and when you bring these two materials in contact, 2D materials in contact with each other, because of the van der Waals interaction, they'll want to stick to each other rather than to stick to materials which are not van der Waals. And then you can assemble very complex devices, not just the 3 layers, but some 8, 9, 10 layers, depending on what experiment you have. We use some variant of this method to also make twisted devices, which I have talked about earlier. So they look like this in an optical microscope. The different colors are basically, these are real colors sort of sensed by the camera. It's because of thin film interference. As you add more layers, the interference condition changes, so you see different colors. But you see, you don't see it, but here outline of different layers of graphene and the gate. And for the present case, we want to make a structure like this, so cross section. So what we identify it, then eventually cut it precisely at the location we want, and put electrodes. You'll see how it looks like that in the real device. And there's a gate at bottom, which is the graphite gate, which tunes the density in this channel. So you can think of this graphene and this gate as a kind of a field effect transistor, and the density of charge carriers in this layer is tuned by this gate voltage. And these are the two superconductors. We use a superconductor called alloy of molybdenum and rhenium. Okay. Now, so we want to, so these Josephson, I guess, resonators, they are designed to have resonance frequencies around few gigahertz, because that's sort of the signal that one wants to amplify. But you can, depending on if you want lower frequency, in principle, you can make your circuit. This is a capacitor, you'll see in a minute, and this is the tunable inductor using the graphene device. And you have outer electrodes to launch the RF in, and the reflected power will be measured to sort of sense the amplification. So the actual device looks like this. This is again 20 microns. So this is the stack of graphene with molybdenum rhenium, and this is two capacitors shunting it. So we don't really have to add a resistor. Some losses in the system will shunt this overall system with a resistance. And this is the external gate, which is underneath, which tunes the density of the charge carriers in here. And that's basically the device. And this is what goes in here. Okay. Now, so effectively, the circuit looks something like this. You have a tunable inductor with some parasitic inductance in series, because the superconductors have an inductance, the kinetic inductance associated with it. And you have this external capacitor, and some internal losses are kind of, I would say, represented as this resistor. Okay. And for these measurements, we do these measurements in our fridge and Vijay's fridge, and most of these final sort of measurements were done in Vijay's fridge, because it's optimized for some things which our fridge isn't yet. So the way it works is that you send in RF signal to different components. This is the amplifier circuit. The signal reflects, and there is this device which is called the circulator. So the reflected signal will come out at this port. So this is circulator is a very common component in RF electronics, and also versions of it are there in optics as well. For physicists, it kind of breaks some time reversal symmetry. So the signals from here comes up, from this port comes here, from this port, any signal traveling comes out here. And then eventually there are some amplifiers. This is the HEMT amplifier at 4 Kelvin, room temperature amplifier, and then either to a network analyzer or to a spectrum analyzer. So this is sort of the DC response of the device. This is the DC current measured as a function of the gate voltage, and this is the Dirac point, which is the point at which graphene has very few carriers, and the critical current, which is the current, supercurrent going through the device, it becomes very small. In fact, on the whole side, it doesn't have any supercurrent flowing through, and that's primarily because of the way we make these Josephson junctions. We do some processing to increase the transparency on the electron side. It actually makes them quite terrible on the whole side. Okay, and this asymmetry was also seen in the data that I showed you. So now the amount of critical current is tunable with gate voltage. That's sort of the tunability part. And the resonant frequency, now if I hook this up in a shunt it with a capacitor, this becomes a tunable inductor. Inductance value changes with a gate voltage. So you see the resonant frequency. This is a plot of the phase as a function of the gate voltage. And you can see that the resonance sending another. Okay. You can measure the gain of the amplifier, and it shows a gain of about more than 20 dB. And something that's the hallmark, which I haven't talked a lot about since the introduction, is the noise that's sort of added in the amplification process is actually quite small. It's about 0.2 Kelvin. And this is the sort of the dashed line is the quantum limit, which is the least amount of noise which is sort of allowed by quantum mechanics. So these amplifiers are operating at the quantum limit. And one can also look at other sort of properties. Whenever you say you have an amplifier, you have to determine other responses of the system. And so this is another aspect of the amplifier, which allows you to determine up to what sort of power these amplifiers work as well as they should be. So that you can bias the parametric amplifier by tuning the gate voltage at different points, and you can see they're not exactly the same, but the gains are close to 20 dB. So, and the center point can be tuned. There are some technical details why the gain cannot be, why the positioning of the biasing point cannot be tuned continuously, because the impedance is not optimized to be 50 ohm at all the frequencies in our fridge. And the bandwidth of this amplifier is about 10 megahertz, which is typical of these single para-amp. The saturation power is about minus 120 dBm, which is comparable to the aluminum. So these oxide-based para-amps, and this performance is basically on par with the aluminum oxide-based para-amps, but now have a tunability with gate, incorporate graphene in their architecture. So I'm going to quickly summarize sort of the key parts of this. So this is sort of the first implementation of. There are not very many parametric amplifiers. After our work, people have demonstrated with other semiconductors this para-amp, but for a long time, people have been just using aluminum oxide-based technology because those junctions are intrinsically actually very, very good. But this interest in using para-amps at large magnetic fields is making people look at different possibilities. What we are interested in is trying to use these amplifiers and the sensor embedded inside. So use the graphene as a sensor and use this nonlinearity to make a sensor which is more sensitive than existing technologies. Okay, in the next 10 to 15 minutes, I'm going to quickly talk about, is it okay if about 15 minutes? I'm going to talk about the second part, which is trying to make bolometers using superconductors. So this field is, I would say, quite old, but there is a renewed interest in it. So, and what the basic idea is you make a meander line, long superconducting wire, and some radiation hits it, the one part of the wire or the meander line, and drives it normal, and you sense that landing of that radiation to infer properties about this. So there are different architectures of this. People have tried to make this embedded inside resonators, superconducting resonators, so you can actually kind of get some natural multiplexing to detect not just also get some sort of spectrometric information. So that's not what we have shown, but another example of a lot of interest in this is trying to make use superconducting nanowire detectors to for searches of interesting, particularly a lot of interest in dark matter searches. These superconducting detectors can actually be very fast, gigahertz frequencies capable detection down to single photon limit. So this is another work that came out after our work demonstrating this bolometric physics. So detection with is one major area. The other area, somewhat more futuristic, is like using in quantum circuits. But there is a lot of interest. So the system that we work with is a high DC superconductor, BISCO. And we started working on it about 5-6 years ago. And these materials, as I said, very high quality materials grown in Tamil Vale's lab here. So it has a complex structure, and I won't talk about it, but the unit cell is about 3 nanometers tall, and people have demonstrated that down to 1 unit cell or half a unit cell, which is basically one side of the copper oxide planes, you get the superconductivity as that of bulk. So the superconductivity in 1 unit cell thick BISCO is the same as that in a bulk crystal. So it's a D-wave superconductor, which is also well known. For us, experimentally working with is kind of common problems of BISCO, which have been known for many years, is degradation is very rapid. So unlike graphene, where you can make a device and come back to and measure it for like 6 months, year, nothing will happen. Challenging to work with BISCO because you have to make the device and cool it down below 200 Kelvin immediately, because then the chemical degradation stops as long as it's below 200 Kelvin, and then you can measure for months. As long as you don't electrically kill the device, you can measure it. And one of the prominent degradation mechanism is oxygen escape. So this copper oxide planes, which is where the superconductivity lives, oxygen leaves these sites, and you get vacancies, and then the material basically, it's a ceramic. And for the interesting anecdote is, like, because I had no experience working with BISCO while making, we learned lots of things, that even to store these crystals of BISCO for over the months of different kind of experiments, the mother crystal is stored at 77 Kelvin to prevent it from degrading. These are all things that we learned while working. So there's a lot of different ways of making superconducting nanowires, which is essentially a narrow bridge of superconductor, which becomes sensitive to external radiation. People use sort of wires as backbone and then deposit superconductor or carbon nanotubes, or use FIB or helium ion based patterning. And the reason why people do all of these is because lithographic processes, which the kind of processes that I described to pattern graphene, you can't use these with BISCO for repeatable results because the processing itself degrades the material. So you can't do. So 2 years ago, we kind of figured out a way to modify the superconductivity, which is essentially the easiest way to describe it is to pattern wires. You do a kind of a rangoli of chromium atoms. So you deposit chromium atoms using a rangoli mask. So it's a stencil mask. So you deposit chromium atoms. When the chromium atoms land on the superconductor, they kill the superconductivity underneath it. And so you basically can make complex structures like you start with a purple colored BISCO thin layer, and I'll show you quickly how it works. Then you put a stencil which deposits green chromium atoms, so you automatically make very narrow wires which are only few atoms thick. So the way one makes these superconducting layers, these are single crystals because they're taken from bulk crystals. Most of the graphene work and other 2D materials, we can use the technique of peeling off with tape. It doesn't work with this material. So we use for this work a technique which is called anodic bonding, which is essentially known in semiconductor industry for many years. And we followed somebody else who actually first, I would say, invented this method for BISCO. So you basically use some glass which has ions inside it, a mobile ion, sodium ions, typically soda glass, and you put the crystal on top, and then you apply a large voltage. And what it does is it bonds weakly these material and the glass because of the application of the voltage and opposite polarity. That when you cleave off the mother crystal, you get very thin layers, a few atom thick layers.
What happens if it's frosted?
Sorry, you don't get very thin layers of the superconductor. It's thickish. Although people have used variants of it, it's working. It peels off, but it's a question of getting thin and large. So this technique, you can get 100 microns by 100 microns or more, which is, I would say, maybe I could be proved wrong, but I think it's not possible with exfoliation. So, you know, this is the kind of device, bolometric device that we have used to study. So you can make devices out of the, you know, big sheet of superconductor and study the wire and measure its electrical response. There is some small change in this TC, but because when you put this chromium, it locally essentially destroys this oxygen stoichiometry, which we showed in our earlier work. So these wires are pretty good, and you know, they show responses similar to the any other kind of superconducting wires, which can be understood within some physics of hotspots formation inside and physics of phase slips. Now, to study the bolometric response, we kind of you know, put this in a optical cryostat where we can shine a light using a laser of different wavelength and different power and different modulation frequency to test its limit. Eventually, you want to sense the photons that are coming in. We use sort of a supercontinuum source, but one of the big advantages of this kind of bolometric detection is that in principle it's very broadband, so it can go far into infrared if you kind of design it. So besides the sort of switching and retrapping physics that you'll see, if you measure the photovoltage, essentially voltage across the device as a response to the light shining on it, that also is pronounced as you bias it at different using different currents. And that's sort of the mechanism for the bolometric response. Now, is the bolometric response uniform throughout this small unit that I'm going to show you in a few in a next slide. So this responsivity of this device is pretty good. There are a large number of these high TC based superconducting detectors. One example I showed you earlier. In our device, our noise equivalent power was not great, and this is something that compared to the other devices that people have recently demonstrated. But this is an aspect that we have some clue about how to optimize in future. But the response is comparable to other such devices. The response is fairly broadband over visible or near visible. Because we had a source supercontinuum source, which we can tune to check. In principle, it can go further on this side for sure, but we at this point we have not really tested it. So it's a good detector with a potential to have a much broader response than what we have tested so far. So to understand what is the source of the photo response, we tried to do kind of measurements on this wire as a function of space. So this is kind of our 1 unit of our, let's say, the bolometric detector. We can raster light at different points inside this. We bias it at a particular point by sending the current through it, sort of the DC current, and then we measure this photovoltage response. So this is the insulating region. This is sort of the chromium deposited on it, and we can measure the photo response as we move. So this is the bulk BISCO. This is also what I say, not bulk BISCO, but extended film of BISCO. There is no bolometric response. Only in the narrow wires you see a strong bolometric response. And depending on the bias point, which is basically kind of demonstrating that it's not a spatially uniform response to the device, but at certain points of the from the electrical response, if there are phase slips or hotspots formed inside the system, they are sensitive to external radiation, and you can detect them. So if you bias it at different points, you will, different parts of the detector, if you have an extended detector, will sense the bolometric response from the incoming light that you have. So it's localized, and one can understand this. If there's even a slightest inhomogeneity in the system, then that particular region has a sort of a weaker extent of the superconductivity and will be more sensitive to the incoming radiation. Yeah.
You're getting signal also from the point screen. Is that like where the
no? So this, oops, no. Okay. So there is some heating. I mean, that is not. So that's a good question. So some part of that is not superconducting, but it can certainly carry heat. So if you drop, something that we don't fully understand, but if the absorption of light there is any different, it will generate heat and still affect the sort of suppression of superconductivity in space. We don't fully understand it. So these are images which are optical images of the simultaneously grabbed of reflection. So you can see this is the chromium part. You can see that there is additional scattering from it. So if there is additional absorption, this is certainly plausible. But we do certainly from the extended films, there is basically no response. Okay, so to understand further, we did experiments on very short wires, which are short segments, and we see basically one single hotspot, which says that these kind of detectors can be designed in different geometries, but if one wants to look at its other properties like responsivity, then as I will show you, it's better to make long ones. So if you look at the responsivity of long and short wires normalized by the normal state resistance, which takes into account, corrects for the geometry, then it makes more sense to make wires which are long meandering wires like the ones that people already use. But this kind of experiment clearly shows that that architecture of making meander wires which are only 1 or 2 unit cells thick is the optimal geometry. So this is sort of the kind of summary of this particular part of the work, and I'm almost on time. This platform of using high temperature superconductor allows you to get to make these bolometric detectors which work very close to at liquid nitrogen temperatures or very close to it, and one can engineer the responsivity. Right now, as I said, one of the drawbacks of our sort of either the geometry has to be optimized or the contacts. The noise equivalent power is somewhat not optimized, and that's something that we want to try. Particularly hooking up these circuits in so that we can launch RF into it and look at detection using RF response is something that we are immediately thinking of doing. Okay, so the broadband nature of the possibility of doing broadband detection using these bolometers is attractive and something that we are interested in exploiting. So this is sort of what I promised. So I want to say a little bit about scalability of these devices and what are the challenges. So in terms of these graphene paramps, they're robust and you can make any number of them. And the most exciting part about those devices is this idea of exploiting property of these 2D materials, as I said, specific heat of graphene, and the fact that the paramp leverages the nonlinearity, has the potential to make some very interesting, potentially a new kind of sensors. Depositing magnetic materials on top would be very interesting as well. And there are other kind of paramps that for other people in the audience, high energy physics people, are already being used for different kinds of dark matter searches. So paramps are quite interesting, not just for the kind of amplification of quantum signals coming from qubits, but there are other possibilities. And with BISCO, we are working on different aspects, and we have some idea on trying to optimize these bolometric architecture. So far, our architecture has been fairly simple, but in future we may couple it to some RF cavities, and that's sort of where I want to stop. The biggest challenge with BISCO, working with BISCO, is, and if you want to make large scale, is that the material has degradation issues. So you have to cool it down to below 200 Kelvin, and then it's stable for a long time. But at room temperature, I would say, as electrical engineers call it, it's kind of a packaging issue. But the temperature is a very important knob. So we don't have a clear solution for it, but typically to demonstrate it and to study it, we quickly cool it down. So when Sanat and others in the lab, Amit and Vilas, they make these devices, they cool it down within 1 or 2 hours of finishing the fabrication. Longer you keep it outside, it degrades.
So what is the advantage of using BISCO when, let's say, YBC or
Okay, yeah, good, that's a good question. So one can use YIBCO. People have used. In fact, I think the paper that I showed also uses version of YIBCO. Growth of YIBCO, if one wants to make some heterostructures of it, YIBCO is harder to do. From what I've never worked with YIBCO, but the difficulty, yeah. Yeah, so I'm not saying that this method offers a huge advantage. So there are papers using YIBCO-based devices. They would be similar. So I think YIBCO is somewhat more stable compared to BISCO. Right? Is that correct? You know more about YIBCO.
No, but that is during growth, not after growth. It has only a problem that moisture destroys it.
Okay.
But that you can deal with.
Okay, all right. That's sort of all I wanted to talk about. I am done. Thank you for your kind attention. If you have any questions, I'm happy to answer.
Thanks, Mandar, for sharing with us really exciting results fresh from your lab, and also some of very interesting examples, which of course some of us also get to understand that these, particularly the sensors that you talked about using for low counting rate experiments like dark matter, NDPD, of course, Vandana is here, could be far reaching in its application. So, any questions from our
In fact, recently there was a call from Moore Foundation to devise tabletop experiments for dark matter searches. The call closed for on October 31st. So I was kind of thinking about it, but it's a bit further away from. I had some small discussions, but there are lots of people who are starting these tabletop. They call it tabletop experiments for different searches.
Interesting. Yeah, very nice.
So you'll see a lot of condensed matter people jumping in.
Yeah. So.
Yeah, great talk. So I just wondering, I mean, for the for your graphene-based this parametric amplifiers, it doesn't depend. Does it have any bearing on the quality of the graphene, like on the mobility or something, or does it not?
Strictly mobility doesn't come in, but the transparency of the junction, the superconducting contacts is the key. So I would say broadly the quality of the graphene plays a role, but I don't have a direct comparison whether CVD grown makes any difference or not. It's sensitive to the contacts. If it's not transparent, the underwave bound states will not form, and then the transparency will be the response of the system will be dissipative. So only in that sense. I don't think there's anything else.
So just another thing I was thinking. So could you also then make the merged element devices like with superconductor, graphene superconductor, and try to tune it with side gate where people do with nanowire? I don't know.
There is with gating there. So we are actually making devices which is basically NBSC2. Ferromagnet NBSC2 kind of devices. So gating is also possible. Right now we don't have devices, but that architecture is eminently possible. There are some other material challenges because the ferromagnets are somewhat finicky. These 2D ferromagnets, they degrade with air and moisture. But the very nice tool that we have is that once you cover it with boron nitride, it buys you a lot of time. Inside the glove box, whatever crazy materials you put on top, and then you put boron nitride, as long as you don't keep them for months at a stretch, you can cool it in the cryostat and study them, no problem.
Thanks.
Maybe you can keep that, just switch off the... we have a couple of questions from Zoom audience.
Yeah, there's Madhavi also has a question. So
okay. Okay, please go ahead. Please go ahead. Please use the mic.
The quality of the graphene that he asked about. So the emphasis is on the contact, and that's why Mori?
Yeah, but in principle, Joydeep might know. This other French group has used NBTN or aluminum. Okay, so there are other materials also which make good contacts. We chose Mori because it makes pretty decent, but we had to work hard to optimize the transparency. A lot of problems we encountered during the lockdown, and Joydeep sort of overcame. So it's but in principle, superconductor it doesn't matter.
Require some sort of milling in between them.
Yeah, it requires.
Mori doesn't need that.
Yeah.
Yeah, you can keep the mic there. Just switch off.
So
let us take a couple of questions from Zoom.
Yeah.
Professor Datar, you can unmute and then ask your question.
I've unmuted. Can you hear me?
Yeah.
Yes, we can.
Okay. No, my question relates to this nanowire bolometers. What is the threshold sensitivity for number of photons? Say visible photons, where the efficiency is peaking. In other words, can you detect, let's say, 100 photons? Is the threshold like 100 photons, or is it 10 photons, or what is it?
Okay, so I will get back to, I have to get back to you about our numbers, but a single photon detection has been demonstrated.
I see.
Yeah.
So it is potentially a good infrared, even detector, maybe one single photon detector.
Yes.
I see. Okay, great. The other thing is about this amplifier business, you said, because you have reached the quantum noise limit. Now, does it apply to only very high frequency signals, or can it be brought down maybe with a different geometry, different materials and so on, to even, let's say, kilohertz or, hundreds of hertz frequencies?
So that's an interesting question. So I think I'll have to think a little bit. So in terms of parametric amplifier, if you make a Josephson resonator which is low frequency, so I may have to amend this, but it should be in principle possible. I don't think there's anything a problem, as long as the resonator, the L and C that you devise. So if you want to go to very low frequencies, the frequency is 1 over square root of L and C.
Yeah.
So if you want to go to very low resonant frequencies, then you have to make your capacitor very large. So those kind of device challenges are there, but I think people make up to a few gigahertz. I've seen. Maybe I think Vijay might know what's the lowest frequency param that has been made. I don't know. Is Vijay? He's not on Zoom.
Not on Zoom also.
Okay, so I have to ask him what's the lowest. But I think in principle, it should be possible. But I don't know what's the lowest that's been demonstrated. But frequency is nothing, like I explained the mechanical parametric. So it's not a quantum. But you can do squeezing and things in mechanical resonators using the same parametric process. So, and those are like 100 megahertz okay. So I don't think there's a fundamental limit, but I need to think a little bit more. This is a good question. I don't know the answer.
Thank you.
Okay. Yeah. Thanks, Acharya.
Yes. Yeah, I have two questions regarding this bolometric detector. One is, you mentioned about the broadband. Does it mean means it is restricted to optical and IR only, or it can go to other photon energies or photon frequencies?
So it can certainly go up to far infrared, maybe at the boundary of terahertz. BISCO has some other interesting responses to terahertz, different physics. There is some Josephson physics because of these layers of superconductor that are superconducting planes. But I think it should certainly go far into infrared without any issues.
Yeah, I have that second question is your superconducting BISCO that is with continued exposure of this light, how stable it would be? It would retain its superconducting property, or its superconducting property would get degraded?
Okay. So as long as as long as the whole system is cold, I don't think it gets degraded due to radiation. It's because this bolometric response is extremely fast, as I showed you in some other groups.
Data.
It's like within a few nanoseconds, it basically cools back down, if you like. So I don't think radiation will degrade it. It's as I said, and other people offered some other strategies of related materials. It doesn't like temperatures about 200 Kelvin or more. Then it degrades.
Okay.
So if you kind of cool it down below 200 Kelvin and liquid nitrogen, I don't see any problem. As I said, long-term storage of these materials of the mother crystal we do at liquid nitrogen.
Yeah. Okay. Thank you very much. Nice talk.
Thank you. Any further questions from audience here? Okay. If not, let us thank Mandar once again for his nice talk. Giving this beautiful picture.
Oh, great. Thanks. Thanks a lot. I enjoyed it. Thanks. Yeah, thanks a lot.
Let me close the